Hello, and welcome to another exciting math video in multivariate calculus. In this video, we'll begin section 15.3, which covers partial derivatives. Now, as I've mentioned in previous videos, we've been building up to this idea of being able to differentiate functions of two, or indeed multiple, more than two variables. So the big first question here is, how do we make sense of differentiating a function of two variables? We'll stick to two variables for the rest of this video. How do I make sense of that? And really the way to answer this is to, well, give yourself a sort of motivating example and then use the tools that you already know. So what's the big tool that we know already about differentiation? And that's how to differentiate a function of a single variable, right? We can get the slope of a tangent line. So long as we have the graph of a function of a single variable, we can grab the slope of a tangent line at any point along that curve. So we know how to do that with derivatives. Let's see if that'll help us make sense of graphs of, or derivatives of surfaces, right? Because that's the graph of a function of two variables. So let's, oops, sometimes it bounces like that. It's like a spring sometimes. Right, so here's our setup. We have a function f of two variables. It's defined on some domain in the xy plane. And f, let's just, for instance, we're going to say that this is the graph of the function f is actually describing a surface in 3 dimensions, and that we can actually go and stand on that surface. So let's say we're standing on the surface of the graph of the function f at the point AB, and then we're on the surface at f of AB. So here's our point in 3 dimensions. AB would just be our point in the xy plane that we're above. So we'll say this is, the elevation above sea level of an actual, ground, and that we can go and stand on it and ask ourselves, well, what is the slope of this surface that I'm standing on? So that's sort of the question someone might ask you naively, to which you might reply, which I might reply, it depends. So it depends on, one, where you're standing. Well, I guess you already told me AB, so maybe that's not a great response on my part, but I just want to remind you, it depends on where you're standing and in what direction are you traveling. Traveling of 2 L's. Oh, my kitty has gotten in the way. Cora. I'll move around her instead of asking her to leave. Right, so it depends on these two things, and most importantly, number 2 here, what direction are you traveling, right? Because now we're standing on a surface, and there's, infinitely many directions that we can travel. So we start with just thinking about just the directions, let's say due east and due north or west or south, right? So just the 4 cardinal directions. We'll focus on just answering this part now. And so here's our situation. Let me zoom out a little bit there. So here's our situation. Let's say we're a hiker traveling on this surface, and we're here at this point on the surface. I'm going to change to black here. And then over here on the left is going to be my mathematical approximation to this surface, just so I can play around over here and get technical about what's going on over here. So we approximate it with this surface. Looks like a hyperbolic paraboloid, does it not? And at this point, right, the idea is I could travel either, let's say, due north or south, so along that direction, north-south direction, or I could travel along the east-west direction. So I could tell you, so what I'm looking for is what's the slope, how is the elevation changing if I head, say, due north. Let's focus on that for right now. So if I head due north along the terrain, so maybe it doesn't necessarily follow the trail looks curvy. If I just travel like due north, maybe I do something like that. And then if I travel due south, I do something like that. So that would correspond to going somewhere on this surface, and then down like that, south on the surface there. So it gives me a curve if I just think about what does my surface do, what does my surface look like if I'm at a fixed x value and I travel either north or south. Fix my x value and travel either north or south, and I get a curve. This is the intersection of the plane x equal, here I'm at x equals 0, right? I'm at the point x equals 0, x equals 0. y equals 0, and then f of 0, 0. So I'm intersecting the plane x equals 0 with the surface, and I get a curve. And now the curve, I can apply what I know of functions of a single variable to understand the slope of that curve, right? The slope of a tangent line at that point, right? So let's say we're at the point 0, 0, and I want the slope of the tangent line here at the curve. Well, I can do that. Well, I need to know what am I different? What is this curve? And how do I, so I need to have like a name for this, right? We want to say like d something dx. But instead, what we do, because we're dealing with this function of two variables, and I've sort of fixed myself at x equals 0, I want that information as well, along with where I am in the y direction, right? So what we say here is that this is this slope of this tangent line. So I'll say slope of tangent line is the partial derivative. I need to really make this curly. So this is not a d, like from Calculus 1. This is a partial sign. Partial derivative of my function f, and I'm traveling in the y direction, and so this is with respect to y. Partial derivative with respect to y at the point, so here I'm at 0, 0. So now, of course, I can plug in different points along this curve. So for instance, this one might be the partial derivative of f, again, with respect to y. My x is still 0, right? I'm still along this curve at x equals 0, so it's x 0, and then what's my y? My y value here, well, it would be something along, right? Something down here. So maybe my y is, I don't know, 2, something like that, let's say, for instance. Or no, let's say in general. Let's say in general, I'm at some point b, right, along this curve. Let's keep it nice and general. So I'm at some point b along the y-axis. And that gives us the slope there, right? That's the slope again. And of course, you could do it back here, but we can generalize a little bit further, right? I could go to any point, right? I could now take, what if I want to do a slice, like, what if I'm standing, let's say, over here, right? So I'm somewhere like here on the surface of this thing. So not at x equals 0, not necessarily at x equals 0. Well, I can come down, there I am at b, and there I am now, let's say, at a. And again, I can now trace out a curve, right? Now I'm going to take a slice of this surface at the plane x equal a, rather than at x equals 0 as we did before. We'll take a different slice, get a different curve, and differentiate that at the point b again, right? At the y value of b. So this, the slope of tangent line, and again, this is in the y direction, and we're at the point AB. This is partial f with respect to, I really got to be better about my partials, right? I don't want to confuse anyone. These are partial symbols, not d's. Partial derivative with respect to y, because we're in the y direction, of f at the point AB. That gives me that. So I can do any point on this surface now. I can understand, I can tell you the slope in the y direction. And so I can tell you how fast the elevation is changing over here as we move either north or south. If I move south, just do the negative of the derivative. So if I want the elevation change to the north, I can get that. Cool. But what if I want to move in the east or west direction? Well, we can do that too, but we're going to intersect the surface with not a plane parallel to the YZ plane, but a plane parallel to the XZ plane, right? We're going to slice it like this to get a curve that runs just in the X direction at some fixed Y value. And again, we can do that at any point. We can take a slice like that, and we get this curve that's now parallel to the X-axis, and we can find a tangent line to that at any point A. And so slope again, of tangent in the x direction, because we're parallel to the x-axis, in the x direction at AB is, and can you, figure out what the notation is going to be? It's the partial with respect to f, or sorry, a partial of f with respect to x. Sometimes my partials look like 2's. Apologize. Partial of f with respect to x at the point AB. So I've now, so what does that look like over here? I should have maybe done that. Right, so this is now in the x direction. I can tell you the elevation change as we just move either east or west. So this is what partial derivatives are. This is the notation that goes along with them. You might also see notation that looks like partial f with respect to x or y evaluated at the point AB, right? And this is the same thing as the slope. The other notation you'll see is fx of AB or fy of AB. Right over here, we could add partial f with respect to y evaluated AB. So these are all notations for the same thing. It's telling us slope in the x direction of a tangent line, slope of a tangent line in the x direction at the point AB, or slope of a tangent line in the y direction at AB. And what I mean by x direction, y direction, again, I'm talking about these planes intersecting the surface and the curve that comes out of that. All right, so that's it for this video. I really just wanted to give you sort of the intuition behind these things. This is what the partial derivatives are. Now the big question is, how do we actually calculate these things, and what's our theoretical framework behind this? That'll come in the next video, but I'll show you right now the definition of a partial derivative. Oh yeah, we got limits. I'll see you there.